Hello there, wind energy students. Dr. John Schrage here, and I want to start talking to you about the part of the chapter 5 today that's about attached and detached flow, or attached and detached flow. Before we do that though, I want to make something a little bit clear. I have to admit I found this part of the chapter a little bit confusing, not in terms of the material itself so much as where was the author even going with this. It took a while to realize, well, part of the story is our author has his actual background in the modeling and simulation of detached flow and attached flow in the context of wind power and so on. And he really was specifically hoping to mention the names of particular models and their authors and so on. And that's interesting and that's appropriate, but that's not really where I want to go with this. I mean, I like to avoid doing things like mentioning the specific names of models that are fashionable at this time or something like that. Or software or anything like that, because that all changes. It quickly becomes obsolete long before you would be, probably by the time the book was published, all that information was obsolete. So we're going to kind of take a slightly different strategy here. But this business of talking about models is not a terrible idea, and I want to make sure we're clear about that, because this business of models can be a complicated idea that I tend to put a lot of weight on when I'm talking to my students in my other classes. People who are survivors of my other classes know that I tend to spend a lot of time talking about the fact that this word model can mean lots of different things. I mean, there's such a thing as a physical model, where the model is literally, it's a simplified representation of a real thing, like a model train. A model train going down the train track, that a child would play with, is not a train. It is a simplified version of a train, but you could learn a lot about real trains using that simplified physical model of the train. Obviously, we don't tend to use physical models very much in the context of meteorology or something like that. We've talked a lot in this course about conceptual models. Conceptual models are like ideas that we're using to represent in a simplified way the real world. And we'll see some examples. I'm just going to review a few conceptual models in just a little bit. Conceptual models might have equations involved in them and so on. There's maybe a simple equation that's describing something, but it is a simplified version of what the real world is doing. If you have taken or will take my Energy 301 modeling electrical load and yield class, you'll know all about statistical models, where we're using past behavior of a system to statistically forecast what it's going to do in the future. Like in that class, we use things like past data about the electrical load under different weather conditions and so on, in terms of how much electricity people are using and so on, to predict what the load will be in future conditions. That's a statistical model. It's using past data to make predictions about the future. And then there's the whole business of numerical models, where you use the basic principles. Like in the case of the atmosphere, that might be stuff like the pressure gradient force, the Coriolis force, friction, the first law of thermodynamics, things like that, to determine what to simulate how the atmosphere or whatever the system is going to change. Just to give you a couple quick examples here, we've been looking at these conceptual models so far in the class. We built a little conceptual model in the last lecture that was about how flow would go over a piece of orography like this little hill here. Or we have had simple conceptual models of like what the wind profile would look like. This happens to be a log wind profile over here. They have equations associated with them. It's not that there's no math. I mean, the word computational model later might make you think, oh, these don't involve computations. But they're different from like a numerical model or a computational model, where we are actually solving the equations of motion that will be describing what the system is doing, or at least coming up with estimates to the solution of the equations of motion. And there's a number of different ways you could frame how these models are going to work when you're going to teach about them. I'm going to follow in here what your book is doing. Your book takes it from the approach of the so-called Navier-Stokes equation. The Navier-Stokes equation looks really horrible because it's got a bunch of awful symbols that you're hoping you never had to see again or haven't seen before or whatever. But it really turns out it's not such a bad thing. The Navier-Stokes equation is basically just a fancy way of saying F equals ma, Newton's second law. Okay, well, let's see, how are we going to do that? Well, the left-hand side of this equation is saying like change in the vector motion of the winds with respect to time. It's actually got another term in there that is, let's not worry about what that other term with that del operator is and so on. But together, the left-hand side of that equation is a way of describing the way the flow is changing. That is to say, the acceleration of the flow, which by Newton's second law means that the other side of the equation is apparently the forces. It's the sum of all the forces acting on the air parcel or whatever. They're going to be, well, it's per unit mass actually, because it's basically what we've done here is we've made this A equals F over M instead of F equals M over A. But, okay, well, what is all that stuff over there on the right-hand side of the equation that apparently is like a sum of forces? Well, I don't love what your textbook did with this here, but the first one of those terms is going to be that's a mathematical way of writing the pressure gradient force. We're not going to get bogged down in all the notation and all that kind of stuff. And there's a term that describes the viscous properties of the atmosphere, the internal friction and so on. Often that term can just be ignored. And then there's another term that, unironically, your book just calls all other forces. Okay, well, I get it. They just basically ran out of paper or something, or you didn't feel like typesetting the whole thing. The point is, it's an equation. And it's basically a fancy schmancy way of saying the equations of motion or Newton's second law or whatever. It's just a particular form that applies under certain conditions in the atmosphere. And like if you're a survivor of one of my other classes where we also talk about models, what you know is that this actually happens to be a way of writing two of the equations that make the so-called 7 primitive equations that describe how the atmosphere works. There are 7 basic equations that describe at any given time what's going on with an air parcel in terms of changes in its motion, changes in its pressure, changes in its temperature, and so on. And that's how numerical weather prediction, that is to say, like forecasting, is done these days, is we use big old computers and they solve things like the Navier-Stokes equation and first law of thermodynamics and so on. And again, if you're a survivor of my physical climatology class or my science of climate change class or something like that, you've learned quite a bit more about how these kind of models work. And this is ugly. I mean, this is not, well, ugly. It's how weather prediction works. It's how our understanding of like climate change comes from and so on. But it is difficult to get insights from this kind of analysis because the math is so complicated. The computer that solved it for you is not going to sort out, oh, well, these were the effects due to Ekman turning of the flow, due to changes in the vertical gradient of the wind speed, and this is changes in stability caused this. No, it just gives you the answer. It doesn't tell you why all these things happened, like all these changes in the wind profile over the course of the day, or how changes in how the flow became attached or detached, and so on. No, the model will just tell you what the answer is. It doesn't tell you why it happened or anything like that. Well, from a meteorological point of view, it's not tremendously exciting as to why tomorrow, well, from a forecasting point of view anyway, it's not terribly exciting why the wind tomorrow will be 12 meters per second instead of 11 meters per second. It's just not important in those contexts. But we're going to be looking for better answers than just like a giant computer chugged through this data and solved these equations and that's what's going to happen. We want more insight. Well, we have other courses that teach about how these kinds of models work and what we can get from them and what kind of questions they can answer and what kind of questions they can't answer. These numerical models are not where I want to go at this point in this class. So, again, this section of your textbook was really trying to talk to you about, oh, the author was saying, I want to talk about the models of attached flow and detached flow, but I don't think that's so important. Instead, let's talk more about what is attached flow and what is detached flow, because I think that is a bit of context that the book wasn't so great about. Alright, so let's start with the easier example, which is attached flow. Now, attached flow is going to be associated with terrain that's either smooth, like out over the ocean or over a lake or something like that, or only features relatively gentle and small bumps. Honestly, real terrain in the real world doesn't really fit that definition all that well. Even other than over the ocean. Over the ocean might be a different story, but almost any features over the land, there's going to be so-called flow separation leading to detached flow, but attached flow is not a terribly bad approximation to what the flow is doing when it is detached anyway. And so again, we haven't yet gotten to what exactly we mean by attached and detached, but first off, to a good approximation, you can usually just say the flow is attached and work with that, because it's going to, in general, be not a terrible approximation to what the flow is doing when it is detached. That being said, there's going to be lots of cool examples of detached flow. So, I mean, we're going to be looking at attached flow either over the ocean or over big open areas like plains and so on. Not where there's a lot of structures, not where there's a lot of hills, certainly not where there's mountains and so on. Now, your book throws out a dictionary definition of the term attached flow that might be helping here. Attached flow, it says, means that the streamlines of the flow follow the terrain and there is no separation. Ooh, I don't like the fact that it defines our word attached flow with another word we haven't yet seen, but let me draw you some figures. See here, we've seen this diagram before in the previous lecture where I just sort of had a little hill there or a mountain or something like that, and I just showed the flow going over it, where the flow was following the terrain. That's what we mean by attached flow. The flow is following the terrain. Now, that doesn't necessarily mean like the flow is entirely parallel to the terrain like I have it right there. I mean something more complex where, like, you know, we saw in the previous lecture where the streamlines of the flow might be getting closer together up at the top of the hill and so on. Okay, but broadly the flow is following the terrain. We'll see when we talk about a detached flow, it gets quite different. Now, as I said, in the real world, practically nothing other than the ocean is going to work as attached flow. But the real flow often is pretty well approximated by attached flow. We're saying the flow, I know the flow isn't really following the terrain. It isn't really coming up to my house, going up the side of the house, going over the roof of the house, coming down this side of the house. Obstacles of the flow are going to set up all kinds of weird flow separation that's going to result in detachments and so on. But I can largely approximate the wind blew over my house. That's attached flow. Okay? So it's not a bad approximation. It's really a pretty good approximation that we actually use quite a bit in, say, weather forecasting. And to understand why we need to do this, we need to come back to our problem about terrain in general when we talk about forces and so on. This opens up an interesting problem. We kind of hinted at this before in the past. If I want to describe the location of some air parcel, horizontally, that's not such a big deal. We can talk about it in terms of its latitude and longitude, or like we could define a coordinate system and it's got an X and a Y coordinate. The vertical coordinate is a lot more complicated to understand as to what we want to use to describe the location of, say, an air parcel in the atmosphere. I mean, the easiest way to do so would be to use a so-called Cartesian coordinate system where we describe how far up our air parcel is in terms of like how high it is above some reference level, typically like sea level or something like that. This word Cartesian comes to us from the philosopher Descartes, who is credited with having developed like graph paper. Okay, he has this idea that like he understood you could describe things in a coordinate system where you have X and Y and Z describing east, west, north, south, and up and down. And so like in this example over here, where I've got some terrain and so on, and that cross-section of the atmosphere, I've labeled 1, 2, 3, 4 heights. I labeled them Z1, Z2, Z3, and Z4. And that would be a perfectly reasonable way to take like two air parcels. One of them's at Z1, some height above sea level, and the other one's at Z4, another height above sea level. And in this coordinate system, we could talk about like the wind. We could say like a U wind was maybe from west to east or from left to right on this diagram right here. And by, if we're at height Z1, we're going to say we have a wind of so many meters per second, and then we'll be at some new location at height Z1, but some different X and Y. That's what a wind is, right? We're following horizontally, staying at a certain height above sea level. We're moving the wind. And that makes really good sense, and that's really an intuitive way to teach about this stuff. But what's going to happen if that height above sea level intersects the ground? Z1 is not all that high above sea level. It's perfectly reasonable that mountains or high country might be below that. What happens then? There is no good analytical solution to that. There might be a force pushing that air parcel that way, from left to right across your diagram here, but that's into the side of a hill. Analytically, that's a very complicated problem to solve. Cartesian coordinate systems for the vertical coordinate are not the only tool in our toolbox. We could also describe them in terms of like an isobaric coordinate system, where we describe the pressure of the height of an air parcel in terms of its pressure. So like, for example, we might have pressure levels, P1, P2, P3, and P4, where there may be the 925 millibar level, the 500 millibar level, the 300 millibar level, or whatever. And then we could take air parcels that are at the 925 millibar level, and we could have a wind on them that will be moving them along that constant pressure level, you know, from one location to another, but they're still at P1, or at the case of that top one, they're still on the pressure level P4. And all of that works really well until you, again, get near terrain. It's hard to figure out how this attached flow is going to work when our forces are pushing that air parcel right into the ground. We know that's not going to happen, but it's awfully hard to figure out how to write like my Navier-Stokes equation or something to describe how that flow works. This is actually a really big problem. It's very hard to figure out how to describe a simple thing like attached flow using the kinds of coordinate systems that are great for teaching, like Cartesian or isobaric. That's why, in practice, real numerical models don't do that. They use a different coordinate system. They use the terrain-following coordinate systems. There's actually that's a whole class of coordinate systems that all work in approximately the same way. We'll talk about a particular variation on that called sigma coordinates. Sigma coordinates are another type of coordinate system where we're describing the height of, say, an air parcel above, you know, how high up it is. But in the sigma coordinate system, you describe the altitude of, say, an air parcel or something like that by comparing the pressure of the air parcel to the pressure at the surface below it, all the way down at ground level. So sigma is just a ratio of the pressure of the air parcel to the pressure at the surface below it. So, like in this diagram here, I have sigma 1 is equal to 0.9. That means that everywhere along that black line labeled sigma 1, the pressure is 90% of the pressure it is at the surface. Or sigma equals 0.7, that is the place where the pressure is 7/10 or 70% as high as it is at the surface. And you could even have a sigma surface at like 1.0. Well, that would be the pressure is the same as the pressure of the surface. That would be the surface itself. And see how this works so slick. I mean, it just means that sigma is just ranging from 0 to 1, where 0 is like the top of the Earth's atmosphere where there's no pressure, and 1 is down at the surface itself. And then if we just take an air parcel at any given sigma level, and we say, hey, we have a wind pushing it from left to right on the diagram, but it's going to stay on a sigma level, at least to a good approximation here. Well, the flow no longer goes into the mountain, it just gladly goes right over it. It follows the terrain. This is a hugely nifty trick, and in fact all the weather prediction models and so on, the kind of things that produce the forecast you see every day on TV and find on your favorite websites and so on, they all in fact are done using terrain following coordinates. They're approximating the flow as like an attached flow that just goes right over the topography. That's pretty slick. Basically, in sigma coordinates, you get to treat all flow as attached flow. And as you're going to see, the detached flow situations are so much more complicated that we get, this is a nice little approximation here. But we got to think about this sigma coordinate thing. Now, sigma coordinates are not going to work over crazy complicated terrain. If you needed to simulate the flow going over and around in, these rocky peaks here in Patagonia, that's not going to work. Okay? But if we want to just work with some simplified version of the terrain to make like a large-scale weather forecast, this could be fine. You know, for example, this diagram here has two different maps of parts of North America and Siberia with two different resolutions of terrain in the model. And you can see, especially the one on the right, I mean, it's a very simplified version of what the real terrain is doing. You can see how there are some high areas and some low areas, but they're all tens if not hundreds of kilometers across with gentle slopes and so on, whereas a higher resolution model there on the left has more details, but all of them are much simpler than the real terrain, which has, you know, complicated peaks and valleys and rock formations and so on. We're just making a simplified approximation to what the flow is doing and saying, let's say the flow stays attached to these simplified topographies. All right. Honestly, other than like the notation and understanding the coordinate system we think about it in, attached flow is really not all that complicated. It's kind of the default idea. It's kind of the simple one. Now, before we move on and start talking about detached flow, let's answer a couple quick questions. When we describe flow as being attached, the wind is blowing A, from areas of low pressure towards areas of high pressure, B, vertically, not horizontally, C, more or less parallel to the surface features of the features at the surface, or D, at the same speed at all heights of the boundary layer. Oh, which of those? None of those are exactly the same words that we used, but which of those would be a good way of describing what we mean by attached flow? Make a choice from those 4 options and get a little feedback before you move on to question 2.